Good morning, Anudal. My name is Anurag Gaurav from EC Department, Vignan Snehra. Today we'll discuss the important topic of our student, that is the analogy between vectors and the signals. Generally, a vector can be defined as which consists of a particular magnitude and the corresponding direction. Generally, we'll first see the concept of analogy between the vectors and the signals. Then slowly we extend the concept of vectors to the signals and the orthogonal signals based in mean square error calculation, closed or complete set of orthogonal functions like that. First, it is a perfect analogy between the vectors and the signals. A vector contains the magnitude and the direction. Let the component of V1 along with the V2 is being given by the C12 into the V2. The component of a vector V1 along with the vector V2 can be obtained by drawing a perpendicular from the end of the V1 to the vector V2. This particular V from the end of the V1, we are drawing a one particular line. That line is the perpendicular line. Therefore, we will have a C12 into the V2, which will be upon to the V2. This perpendicular line will be given as V1 is equal to C12 into V2 plus VE. There where VE is the error vector, where VE will become our error vector. This is the one possible way of drawing the corresponding vector from the V1 to the corresponding V2. Therefore, we get a component called as the C12. This V1 is equal to C12 V2 plus VE. There are another two possible ways of drawing the component from the vector V1 to the V2. That will be given by like this. That is the first one as the vector which is not the perpendicular and upon to the V2, that is C1 V2, from the V1 to the C1 V2, and similarly from the V1 to the V2 which is beyond the perpendicular. First is below the perpendicular and then one is the beyond the perpendicular. In both the cases we have the V1 can be written as the sum of the two vectors, that is C1 V2 plus VE1 in the first case. In the second case, that is the V2 is equal to C2 V2 plus VE2. That is the second case, where VE1, VE2 and previously VE will be nothing but our error vector, where while this error vector will be obtained by drawing our component from the V1 to the V2. Next, this is the concept of vectors. This concept of vectors will be similarly implemented upon the signals. Here we consider the V1 and the V2 vectors. In the signals we consider the two functions f1 of t and the f2 of t. Let us consider the two signals f1 of t and f2 of t. That is, we can approximate the f1 of t in terms of f2 of t as being given as f1 of t is equal to c12 into v2 plus certain error function similar to that of the error vector there. V1 equal to C1 to V2 plus VE. Here we will write the F1 of t is equal to C1 to F2 of t, Fe of t, where Fe of t is equal to F1 of t minus C12 into F2 of t. One possible way of minimizing this particular error is by integrating over the interval of the t1 to t2. That is 1 by t2 minus t1 integral of t1 to t2 Fe of t dt. Similarly, 1 by t2 minus t1 integral of t1 to t2 f1 of t minus c12 into f2 of t dt. Next, this particular one can be this f1 of this particular error calculation will get a one particular positive values in the positive time and negative values in the negative time. These positive values and negative values will get cancel each other. Therefore, indicating the total error has been 0. But it is not the correct value. Hence, to produce that particular positive and the negative values as a particular finite error, we'll take another choice of calculating the error, that is nothing but our mean square error, where we'll take the square of the error function, that is E is equal to 1 by t2 minus t1 integral of t1 to t2 f square of t dt, where f square of t dt will be called as the f1 of t minus c12 into f2 of t whole square. This whole square can be written as similar to that of the fashion of a minus b. Before going to that, we need to have an error such that the value of the C12 should be getting such that the error will be as the minimum. For that, what we need to take is we need to differentiate the error expression with respect to the C12 and made equal to the 0. This d by dC12 of the error will be equal to 0. What is the particular error expression? It is 1 by t2 minus t1, integral of t1 to t2, f1 of t minus c12 into f2 of t dt. This a minus b whole square will be written as a square f1 square of t minus 2ab minus 2 into f1 of t c12 into f2 of t. And the b square is c12 square into f2 square of t. As the first part is the f1 square of t, which is not varying with respect to the c12. Therefore, this particular term will be 0. Therefore, the next term is the 2 into f1 of t, c12 into f2 of t. Here 2 into f1 of t, f2 of t are the constant, and the c12 will be the variable varying with respect to the c12. Therefore, while differentiation will get a 1 here, remaining all are the constants. In the third term, we have the c12 square. While differentiating that c12 square, therefore, we'll get the 2c12. This particular 2c12 is the third term, and f2 square of t dt as to will be present for the integration purpose. Therefore, the next step what we'll get it is integral of t1 to t2, 2 into f1 of t, f2 of t dt, plus 2 into c12, integral of t1 to t2, f2 square of t dt. This 2 on both sides will get cancelled. While simplifying for the c12, we'll get the integral of t1 to t2, f1 of t, f2 of t dt by integral of t1 to t2, f2 square of t dt. Where the c12 is nothing but our component, which minimizes the mean square error as g, mean square error as minimum. One more important point is that the component will be 0 when the two signals are said to be orthogonal. That is, the c12 is 0 to get the condition for the orthogonality. That c12 is being substituted as 0, integral of t1 to t2, f1 of t, f2 of t dt by integral of t1 to t2, f2 square of t dt. And the denominator term will be 0. That the integral of t1 to t2, f1 of t, f2 of t dt will be equal to 0. That will be equal to the corresponding as 0. Next, this particular expression, next the same concept will be implemented for the mutually orthogonal function, that is f1 of t and f2 of t. The same concept will be extended to the n number of orthogonal functions. Like the orthogonal functions will be from x1 of t, x2 of t, and so on xn of t over the same interval of t1 to t2. Now, in these orthogonal functions, consider the two functions like xj of t and xk of t to satisfy the orthogonality condition. That is, integral of t1 to t2, xj of t, xk of t dt is equal to 0 for the j not equal to k, and integral of t1 to t2, xk square of t dt is equal to kk. It is the particular function. Let the function f of t can be approximated with this orthogonal signal space by adding the components along mutually orthogonal signals. Let the f of t will be approximated with the n number of functions like x1 of t, x2 of t, and so on xn of t. Therefore, the expressions will be given by the f of t is equals like this, as f of t is equal c1 x1 of t plus c2 x2 of t plus and so on cn xn of t with plus fe of t, where fe of t will be nothing but f of t minus summation r is equal to 1 to n cr into xr of t. This fe of t is used in calculating our mean square error, that is e is equal to 1 by t2 minus t1 integral of t1 to t2 fe square of t dt. The component which minimizes the mean square error is being given by here the components can be 1 to n values, that is de by dc12 equal to de by dc2 plus equal to and so on de by dcr, which is equal to 0. This de by dck will be equal to 0. D by dck of E is nothing but our mean square error, which is nothing but 1 by t2 minus t1 integral of t1 to t2 fe square of t dt, which is equal to 0. Then the d by dc12 of 1 by t2 minus t1 integral of t1 to t2 f of t minus summation r is equal to 1 to n cr into xr of t whole square dt. This particular again it will be in the fashion of a minus b whole square, which will give the The same simplification, a square minus 2ab plus 2ab, and the components which does not consisting of the components, it will be led to the 0, because the component is not being mixed, then the differentiation value will be the 0. That's why the first term will be left it off. Then we'll get the integral of t1 to t2, 2 into f of t, xk of t dt plus 2 into ck integral of t1 to t2, xk square of t dt. Then the ck is equal to integral of t1 to t2 f of t, xk of t dt, and integral of t1 to t2 xk square of t dt. Then the integral of t1 to t2 f of t xk of t dt, which is equal to ck into hk. Okay, where this particular denominator term will be nothing but our k. Then the mean square error calculation. In the mean square error calculation, it is the square of the average of the square of the error function f of t, which is nothing but our mean square error. It is generally represented as e, which will be called as epsilon. Then e will be equal to 1 by t2 minus t1 integral of t1 to t2 fe of t whole square dt. Next one, this particular fe of t will be split as f1 of t minus summation r is equal to 1 to n cr into xr of t whole square dt. Again the a minus b whole square form, a square f square of t dt minus the x plus b square, that is cr square into xr square of t dt second term, and the minus 2 into cr into xr of t f of t dt. Now in these calculations, the second term, observe the second term, what we have is cr square into integral of t1 to t2 xr square of t dt, and which is equal to cr into integral of t1 to t2 xr of t f of t dt, which is equal to cr square into kr. Therefore, substitute these values in our above integrations. Therefore, what we'll get here is 1 by t2 minus t1 to t2 f square of t dt plus summation r is equal to 1 to n cr square into kr minus 2 into summation r is equal to 1 to n cr square into kr. Then f square of t dt minus summation r is equal to 1 to n, that is in the above expression, that is the plus cr square into kr minus 2 cr square into kr. That's why minus cr square into kr. Then cr square into kr can be written as c1 square k1 plus c2 square k2 plus and so on cn square into kn. Then the closed order, next topic is the closed order complete set of orthogonal functions. For that, let us consider a set of n mutually orthogonal functions like x1 of t, x2 of t and so on, xn of t over the interval of the t1 to t2. Now this particular orthogonal set is not sufficient, is not a full-fledged orthogonal set. It will become a closed or complete set of orthogonal functions when our existing function f of t also satisfies the orthogonal function. That means f of t should satisfy the orthogonality with the n number of functions. Therefore, the integration that it should satisfy is the integral of t1 to t2 f of t xk of t dt is equal to c. That one. And the f of t is said to be orthogonal to each and every function of the orthogonal set, and this set is incomplete if the f of t is not included. If the f of t is been included, then it will become a closed or a complete set of orthogonal functions. Next, when the f of t is been included, then the more number of terms will be implemented in our approximation process. If we implement the more number of functions, like f of t is equal to c into x1 of t plus c2 into x2 of t plus and so on cn into xn of t plus e of t. If these approximation is not so, where we cannot get the error as very less, then add the number of terms to the n from the n to the infinity. That means if you use an infinity series which converts the f of t, which produces the mean square error as being 0. Next one is the orthogonality in the complex functions, where orthogonality in the complex function such that the two functions f1 of t and f2 of t are the two complex functions. Then f1 of t can be expressed in terms of f2 of t, which can be given as f1 of t is equal to c12 into f2 star of t, where this f2 star of t is the complex conjugate of the f2 of t, where while calculating the c12 also we will get the same thing, that is integral of t1 to t2. First function is as is f1 of t. In the second function, in place of f2 of t, will replace with the f2 star of t, and the denominator also the second function as is, that is f2 star of t whole square, while squaring will take the magnitude. And while considering the orthogonality condition, that is the C12 will be equal to 0, then the f1 of t will be f2 of t will be the orthogonal condition, which is being given by the integral of t1 to t2 f1 of t f2 star of t dt. These are the concepts what we have seen here, that as analogy between vectors and the signals. Next one as the signals concept, the orthogonal signal space. Next one, orthogonal signal space. Next, mean square error calculation, closed or complete set of orthogonal functions, orthogonality in complex function. This is the end of the first unit. There will have, these are the topics which will be ending with the first unit. Thank you.